Okay, chapter 4, section 5 is proving triangles congruent by SAS and HL. Two different ways. So we've got, right now, what we've got under our tool belt is SSS. If I can prove that two triangles have three sides that are congruent to another triangle that has three sides, those three sides congruent to those three sides, well then those triangles are congruent. But now here are two new methods that are also shortcuts. One called SAS. What do you think SAS might stand for? Side, angle, side. Now notice that the angle was in the middle. It's in the middle of the two S's. That's not by accident, that's on purpose. It has to. It's not because they didn't want to rearrange it another way and have a bad word. Like that bad word is not like a method that we can use in geometry. This one is an exact is a way of proving two triangles congruent. And the last one we're going to talk about today is called HL, which stands for hypotenuse. Bless you. And leg. Hypotenuse, leg. So we've got SAS and HL. Hypotenuse, leg. Okay, so before we get into SAS or any of the others that we're going to talk about, we need to talk about this word included. We're going to talk about included sides and included angles. When we have an included side, if we ever talk about an included side, it means it is a side that is between the given angles. For example, if I give you two angles, I'm talking about the side that is in between those two angles. For example, notice here it says side AB is included between A and B. Here's A, here's B. Notice that in between those two angles, like in between them, if I were to play connect the dots, is this side AB. So this is something that we call an included side. It's between two angles. If I give you two angles, that is the side that is included. It is between them. When we talk about included angles, it is the angle where the given sides meet. So let's say that we're talking about AC and CB. Where those two lines meet up, where they meet up, kind of like chopsticks pinching a piece of food, is an angle. Which angle is where those two lines meet up? Angle C. It's kind of right there, right in between them. I shouldn't have made these angles congruent there. I don't know why I did that. So right there, we've got angle C is an included angle. If I tell you, like, what is the included angle for AC and CB, well, you just look, where do they meet up? Where they meet up is an angle. So we're going to be talking about included angles and included sides. Without that terminology, the rest of this is not going to make sense, because we're going to be talking about very specific angles and very specific sides that have to be certain things. So we're going to be talking about them. So when I say included, it means it's between two of the sides. And when I say included included sides, then it means it's between two of the angles. Yes, ma'am?
Do you have to write the lines in a specific way?
No, you could write it CA or BC. Okay, so here comes our next postulate, the SAS postulate. SAS. This is a new thing that we can use on proofs. If two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. This is a way that we can guarantee that two triangles are congruent. And that might look like this. Here's triangle ABC. Here is triangle DEF. So in this new method, how I could prove these triangles are congruent is, let's pretend that I told you that AB is congruent to DE. And I also told you that BC was congruent to EF. Well then, if I only have one more angle, I can prove that these two triangles are congruent. But it has to be a very specific angle. Which angle am I interested in on the left triangle? B, because it is where these two lines meet up. It is the included angle right there. I need this one to match which one on the other triangle? E, that is the included one on this one. So the reason that we call it side angle side, because here is a side with an angle in between and a side on the other side. We've got a side with an angle in between and a side on the other side that match. If I were to take two pencils, like I'd have to use some ones that are unsharpened here to kind of illustrate this point. Let me see if I've got 4 unsharpened here so you can see it in the real world. 1, 2, 3. Really? I don't have this one? I do. I'll go get one. So if I were to have some lines that I know are congruent to each other. All right, so in my right hand, I have 2 unsharpened pencils, and I used unsharpened because I want them all to be the same length. And in my right hand, I've got 2 sharpened pencils. The only thing that's controlling how long the other line is the angle. Like, right? Because if I've got 2 unsharpened pencils in my right hand and 2 unsharpened pencils in my left hand, these lines are congruent to these lines, right? They're all the same length, right? I mean, they're all the same. The only thing that's going to change the shape of the triangle at this point is the angle where my hands are. That included angle. If I open that up more, it changes the triangle size. If I close it, it changes the triangle size. So as long as I match the angles in both hands, I end up with the same triangle. That's SAS. So that's why that third side doesn't even matter there if I have the angle in between, that included angle. All right. So before we get into HL, we need to talk about the parts of a right triangle. These are only the things, this terminology that we're going to use only are words for a right triangle. You will never see these words on a triangle that is not a right triangle. First of all, we've got the legs. The legs of a right triangle are the 2 parts that touch the 90-degree angle. So notice the legs always are touching the 90-degree angle every single time. Whereas the third side, the longest side of this triangle, it will always be the longest side, is called the hypotenuse. Sometimes people have a hard time just remembering which one is the hypotenuse. I always use this little trick here. That right angle is an arrow that points at the hypotenuse every single time. It always points at the hypotenuse every single time. So if you want to know where the hypotenuse is, use the right angle. It is an arrow that points at the hypotenuse. So no matter where I turn this triangle, no matter how I flip it, that right angle will always be like the tip of an arrow that points at the hypotenuse. So when we talk about HL, that is one of the things that we are going to use to determine whether 2 triangles are congruent. If they are right triangles, you can only use this HL thing that we're going to do when it is a right triangle. So here comes the HL theorem, the hypotenuse leg theorem. And biggest thing, you can only do it when it comes to right triangles. If it's not a right triangle, don't ever say HL. If the hypotenuse and a leg of one triangle are congruent to the hypotenuse and leg of another triangle, right triangle, then the triangles are congruent. So here's what we've got. If we've got a triangle that is a right triangle, and you can show me that the hypotenuse is congruent to the hypotenuse, and one of the legs is congruent to another one of the legs. I don't need both of them. That's why there's only one L. I only need one. So let's say that I could show that this one down here is congruent to this one down here. For HL, this is enough to prove that they are congruent. Yes, ma'am?
Let's say you said that the bottom leg is congruent to the left leg.
Okay, so let me redraw it then so that it looks like, because I can't do that with this picture. I can do it though, I can do exactly what you want, but I have to change the picture then. Then it would look like this.
No, but I'm saying like if you have the same triangle here, hold on, let me show you. Like instead of having this line be congruent to this line is going to be congruent to this line.
Well, but that's what I did. Like the thing is that when I can't have two different things. Like see how this one here is the longer line? Like I drew it longer, so I couldn't make the short line congruent to the long line. That wouldn't make sense. You know what I mean?
Okay.
So what I could do is rotate it so it was on the left like you wanted there. So like what I've got is that these two are the same sides right there. That I've got these two are the same sides. So there's only two options that when it comes to legs. Either that both of the legs will be exactly the same size. It is possible that we could have a right triangle that looks like this. That is a very special kind of right triangle. But remember, what we're looking for here is HL, one leg and the hypotenuse. But this is not enough to show me the hypotenuse is congruent there.
Does it matter like which leg you use? Like,
Nope. As long as you can prove to me that one leg matches one leg and the hypotenuse matches the hypotenuse in a right triangle, then that's all you need. So it doesn't matter which way they're rotated, as long as you can prove to me that one of the legs, one of the ones that's touching the right angle, matches another one that is touching the right angle, and the hypotenuse matches the hypotenuse, then these triangles are guaranteed to be congruent. Okay, here's where this gets interesting. We know SSS, we know SAS, we know HL. I'm going to make notes of this here. SSS, SAS, and HL. This is the what we've got so far to prove that these are congruent. So we're going to state which congruence methods can be used to prove the triangles are congruent. If none, state NC. They mean not congruent, but really what they should say is not enough information. So let's look at A. So I'm going to make you prove whatever you say. I'm going to make it you prove it to me. What?
Yeah, I mean, I was going to put the third angle one, but that wasn't one of the ones that we learned.
Okay. Colette? Okay, so let's just see the things that we do know. Now, there is one piece of hidden information here that I know that something is congruent that they're not showing. It's one thing. Amber, what do you got?
The HL one, because you have one of the legs and then they're sharing a hypotenuse, so that they're automatically going to be congruent.
Okay, so let's talk about a couple things. Why am I totally against HL from the beginning? From the beginning. There's nothing that shows me it's now it may be a right triangle, but there's nothing that shows me that.
SAS.
Okay, so why SAS?
Because though it doesn't show that there's another side that's equal, that they share a middle line. Which
Okay, so here's what she's saying. She's saying that this side, remember, because of the reflexive property, is congruent to itself. So she's showing that there is an angle on the left that is congruent to an angle on the right. There is a side on the left that's congruent to the side on the right, and the blue one is a side on the left and the side on the right. So actually, I am not okay with SAS on this one, even though it totally feels like it should be. Why am I not okay with SAS on this one?
Because the outer angles, we don't know that they're congruent.
What do you mean the outer angles? Well, these are definitely shown as congruent right here. That's shown as congruent. That's definitely true.
It's not included.
It's not the included angle. I'm going to tell you right now, if we said this in the order it is, if I spoke this word out loud, I'd get in some big trouble because this is angle side side. And if I were to write that down, then I'm writing some bad words in geometry. So angle side side is not a thing. The angle that we would need is between the two sides. So here's where the red and the blue meet up. I would need that angle, and the red and the blue up, I would need that angle, which I don't have. Colette. Isn't what automatically proven?
Isn't it like automatically that is a 90 degree?
Why?
Because they're linear pair.
Linear pair could also look like this. Are these 90? That's a linear pair as well. So a linear pair just means it's two adjacent angles with sides that are opposite raised that are going to make 180 degrees together. The truth is, I don't have enough information for this. It looks like I do. Right now, the way we're at now, right now, I don't have enough information. So I'm going to say not congruent. All right, so we get to this one. Let's see what we've got. Yes, ma'am.
Okay, this one's HL because it is a right triangle, two right triangles because it's automatically 90. And the hypotenuse is the same on both, and they share a line, so
That's what I was looking for her to say there. So first of all, I'm glad because a lot of times people look at it and they go, wait a minute, is this ASS again? And you're like, no, this is not that because this is a right triangle, which allows me to say maybe, it doesn't mean it's a guarantee, maybe these are HL. And that's exactly what you notice. The hypotenuse matches the hypotenuse. And this line, the reflexive property down the middle, allows the L that I need as well. There's the L, there's the H. This is HL, but she could only do that because of this, because it was a right triangle. This is HL for sure. Let's talk about C. Yes, ma'am. Ooh, this is an interesting one.
So the angles in the middle are like congruent because of vertical angles.
Okay. Let me just notice that I'm making them with 3 lines because I've already got one with 1 line and I've already got one with 2 lines, so I'm not going to use 1 or 2. That's why I'm using 3. It's just poorly drawn. Here you go. There's the. It's really hard to do these in PowerPoint, so whoever made this, just there you go. Is that a little better? That's what we're looking at there. So what do we got?
I was gonna say about like third angles.
I was going to say, why am I wrong when I say third angles? Because I would have thought that somebody would be like, yeah, definitely third angles theorem. So tell me why I'm not right about this. I'm going, look, I've got 2 angles on one triangle, 2 angles on the other, so it's a guarantee that this last one is congruent to the last one. Why is that a bad, like I just did something bad there. I didn't do something. I did a bad thing. Yes, sir.
Because the bottom 2, there's 1 line on one, or there's 1 on one and then 2 on the other. So those 2 aren't.
They don't match. Third angles theorem only works if 2 angles on one matches 2 angles on the other, and we don't have that situation. So we've got a side, we've got an angle, but that's all we've got. We don't have anything else from there.
What about side angle side? Because we know that one side is congruent, and we know that the angle, the vertical angle is congruent. And then if they're congruent, then they're probably the
Okay, so let me go along with that. So I would be okay with side angle side, but side angle side, remember, in side angle side, the angle has to be included, meaning it's in the middle, meaning that this side and this side would have to be congruent. And then this side and this side would have to be congruent. Because the included angle means the angle that's in between there. That's the one we're looking for, which we don't have there either. Yes, ma'am? No. So like these 2 pencils right here are congruent, right? They're the same size. But I could put them 100 different ways, and only one way ends up parallel. So good thought. Doesn't work on this one. Okay. Yep. We don't have enough information on this one. Colette, you want D? Why?
Because the line in the middle is automatically congruent to its side.
Which property tells me I can do that?
Reflexive.
The reflexive property.
And so then, because that angle that they said is congruent, like above congruent, it's included in between the 2 sides.
Good. We do have side angle side here, and it's most important that this angle, where it is located, it must be where the two lines meet up, and it is in both cases. On the triangle on the left where the red and blue meet together, there is an angle. On the right where the red and blue meet together, there is an angle. So we have side, angle, side, side, angle, side. So sometimes it's easier to, instead of having to try to find all the angles and all the sides, we have some different methods now. We have side, side, side. We have, oh, good, we've got angle, angle, angle here. Is that one of our methods that we've learned to find that triangles are congruent? No, and it's not a method. It doesn't exist. That is not a thing. Please lock these words in your head, because it's the number one thing that people want to do is say angle, angle, angle. Remember that, like, when I take these three pencils and I put them together, like these three unsharpened pencils, it is a guarantee to me that they will be an equilateral, equiangular triangle. Why? Because the pencils are the same length, they're equilateral, it will end up as equiangular. However, three toothpicks will also be equilateral and equiangular. They will have the exact same angles, even though they're different sizes. So we have to be careful with this one. So, what else can I do with this?
Can you do the HL thing because it's a...
Prove it to me. Take it. HL. Let's go. It's a good thought. She saw that.
If it's equiangular, then it's automatically equilateral. So then that tells me that...
But are these equiangular?
Yes.
Equiangular means all three angles in the triangle are exactly the same. That's what equiangular. What you're using the term as if like the two triangles have equal angles to each other. They do have congruent angles to each other, but that's not what equiangular means. Equiangular means inside a single triangle, all the angles are congruent. Colette. Not enough info here. So this is actually kind of good that there's not a lot of info on these, because you go, okay, well, I know what I need to look for now. We've got side angle side, we've got an HL, we've got a side angle side. So 3 of them we could do, 2 of them we couldn't, even though we had lots of information there. Sometimes it feels like we've got so much information, but it may not be enough. Now, don't worry, there's actually more shortcuts than these, but we got to give them to you in doses. Yesterday you learned 1, today you learned 2. There's more after this as well. All right, is there enough information to prove the triangles are congruent? If there is, state the postulate or theorem. They are saying, now we have to be very careful with this. Watch this. Triangle ABE is congruent to CBD. So ABE, this is a tough one because these are going to overlap. And CBD. Okay, this is not a proof, so that's kind of good because this one might be a little bit harder as proof. But let's talk about the things that we know. If we're going to prove in one of our methods, like if we're going to prove that these two things are congruent, I can use SSS, I can use SAS, or I can use HL. Guess which one of those three it's probably not going to be? It's probably not going to be HLY. I don't see anything that even looks like a right angle in there, so it's probably not going to be HL. So we're probably down to one of these. And of those two, which do you think is more likely in the scenario? Why is that one more likely than the other one? There's some angles going on. So they're giving me some angles. Maybe it has to do with angles. Now, it's not a guarantee, but those are the ones we're looking at. I'm just going to clean up my lines here a little bit. I'm not happy with the way they look. So start taking a look at it, and let's figure out how we can figure out whether these triangles are congruent. A, B, E, and C, B, D. That's what we're going for. All right, let's talk about the things that we know. Yes, ma'am.
So we know that angle ABE is congruent to angle.
What was the first one? AB what? AB?
D.
AB?
E. No, D.
Okay, ABD is congruent to?
CBE.
CBE, angle CBE. Okay. But notice that is not the whole angle of a triangle. So like if you look at the yellow triangle there, that's not the whole angle up there, nor is it the whole angle of the red. Now don't get me wrong, You're not giving me bad info. Just it may not be enough info to be the angle that we need. So let's keep this like on the back burner for a minute because I have a feeling we're going to have to come back to this. Let's talk about some sides because the sides are a little bit easier. The sides are easier to address than the angles.
Angle AB is congruent.
Do you mean side?
Side AB is congruent to side CB.
Side AB is congruent to side CB. So one side of the yellow triangle is congruent to one side of the red triangle. Anything else? Yes, ma'am?
Side, I don't know if it's really side, but could you say like BD is congruent to BE?
Yes, side BD is congruent to side BE. That's one side of the red triangle and one side of the yellow triangle. So here's what we've got. We've got on the yellow triangle two sides matching up with two sides of the red triangle. But what we need is an included angle, and unfortunately this is not enough to do it because look at the yellow triangle. This right there is not the whole angle up top. It's missing this part. And this one right here is also missing that same part. Now, I don't need you to prove it to me, but there should be some logic as to why those angles are in fact the same. Yes, so he's saying that dotted line there is still part of the yellow angle and it's still part of the red angle.
So it wouldn't be wrong to use it.
Well, we're going to need some more information as to prove it. Why? There's nothing that says, there's nothing that's blatantly, here's what we would need to prove it. I would need this, something showing me like this. That's the yellow angle up top to this one. But actually, we don't need to do a whole proof. Let's think about this. Why is it a guarantee that the yellow one up top is congruent to the red one up top? Keep going.
No, I was going to prove why the yeah, okay. So ABD and DBE equal ABE. So just
Okay, so let's see. Angle ABD, that's this one on the left here. And angle what?
DBE.
And plus angle DBE are equal to what? What are they equal to?
ABE.
Angle ABE. Now, we don't need to do this as a proof, but what allowed you to do that?
They're like the basic angles.
So we have a name for that, where those two pieces of cheesecake add up to the bigger piece of cheesecake. The what? Angle addition postulate. Do the same thing on the red one for me now. Same thing.
DBE.
Angle DBE
Plus
plus EBC. Sorry, angle
equals DBC.
equals DBC. So, notice that these two statements, they have something in common, don't they? What do they have in common? They both have a DBE. I'm going to do something real quick. I'm going to get DBE all by itself. I'm just going to do some subtraction. I'm going to do some subtraction from both sides. So I've got angle ABE, that's this one here, and I'm going to subtract ABD from both sides. Actually, let me do this the way that's just like it's written. Sorry, I'll make this easier for you guys. Angle DBE, that's this one. And I'm going to subtract away ABD from the left, and I'm going to go angle ABE minus angle ABD. All I did was subtract that from both sides, okay? On the right-hand side, I'm going to do the same thing with DBE. Angle DBE is equal to angle DBC minus EBC, angle EBC, which means that these two things here must be equal to each other. The combination of those two angles must be equal to each other. But let me just show you why that's totally true without even any proof. Let's make up a number for these two red lines here. Like this line right here, let's just make up a number. Let's say it's 30 degrees. And that makes this 30 degrees, right? Let's use a number for that dotted line. I don't care what number you use. Let's use that dotted line, make up a number for it. What number is it? Let's call it, 70 seems a little big. Let's call it 50, okay? Well, isn't 30 plus 50 the same as 30 plus 50? They're both adding the same thing. If we're both taking the same thing. The red one is a congruent angle plus the 50. The yellow angle has a congruent angle plus the 50. So we can do this as a proof, or we can do it during logic, like just using logic, but we did not need to do it as a proof here. I just wanted to show it a couple different ways. This is definitely SAS. The included angle here, it matches the included angle here. All right, don't worry, the rest get a little easier. Is there enough information to prove the triangles are congruent? If there is, state the postulate or theorem. Talk to me about this one. Sir. HL. Talk to me about why HL. Both right triangles. When you say side, which side are you referring to? GH and JK. What do we call these pieces of a right triangle? The legs. Okay. So we have the L part taken care of.
And then the hypotenuse HK and FH are congruent as well.
And that's my H. That one was super easy. Now they're not oriented the same way, but we still have HL. The hypotenuse and a leg in a right triangle, which is exactly what we need. I can come back afterwards. I just got to make sure I get through. Last but not least, state a third congruence you would need. So it's saying, what would we need after this? They're giving us some pieces, and the third thing should help us prove SAS. Well, let me go through and mark the things that they've given us first. ST, YZ, RS, and XY. Imani.
Angle S is equal to angle Y.
Angle S and angle Y. Why those angles and not other angles?
Because those are the equivalent.
Has to be the included angle, meaning the angle that is being pinched between the two lines that we're talking about. The ones that are congruent, if we're going for SAS, we need the angle to be in between those two lines. And again, if it helps, I always think of them like, I don't know if you guys ever go out for like hibachi, and when you do, like I always try to use chopsticks. I'm not very good at it, but I always try. And you have to like really pinch your food to pick it up there. So that's the angle we're looking for, the one that is pinched between it, the included angle.